It's insane. I've been married for a long time, and during this time, until today, I never really noticed it, but Mrs. Holloway is a star. Not figuratively, she's literally a star, which is why I'm so gosh darn attracted to her. Cool. All right, welcome back, physicists. So, looking at these, we had problems 18, which, gross. 18, what are some of the others? Because I don't remember. Well, that's reasonable. 22 and 25. Okay, 18, we will discuss. Whether it's right now or in a minute, I'm okay with either. Let's look at the other three first, and then we'll come back to it. Chairs in an orbiting spacecraft are weightless. If you're on board of that spaceship and you were barefoot, would you stub your toe if you kicked a chair?
No, it would still hurt, but it wouldn't.
I think it would feel the exact same. Because you have gravitational mass, which they're clearly not experiencing because they're weightless around the planet, right? But there's another type of mass that we talked about. Gravitational mass is like the scale pushing down. What's the other kind? Inertial mass. Is it the same mass of the chair? Like, it's the same chair just taking the space, right? So it better be the same mass. It's not going to push down on a scale, but it does have the same inertia, which, just as a reminder, inertia is how hard is it to push something. Here, the only thing that would be different is they don't specify, so there's a bunch of answers. If your chair on Earth were on a frictionless surface, you're not going to get any additional forces that are needed to move it, right? Because the force of friction would add to it. You would still stub your toe because there's still inertial mass up in space. It would not probably hurt as bad as if I stub my toe here because the carpet's going to produce the friction. But just the desk itself will still do it because it has inertial mass. All right, number 22. Why is Einstein's description of gravity called a theory? Yeah, hit it.
Was it a law? It's just describes what happens. Theory is explaining how it does.
Cool. Newton's gravitational theories say here's gravity, it exists, and this is how it works. Like, here are the formulas for it. Newton's idea is here's how it works, and one more little further extension.
Under certain conditions.
I can be more vague and still get it. Newton says what happens. Einstein said why it happens. Einstein's big idea was that space-time is curved. That's not the what is happening. That's the why gravity happens. All right, 25. Love this question. Okay, this one. If you guys are into space stuff, there's a game that I would recommend getting if anybody's like ever contemplating working at NASA or with rocket stuff just in general. It's awesome. Kerbal Space Program is like the best game you'll ever find if you're into that sort of stuff. It is like a realistic, let's launch satellites, planets, and stuff. It's on a much smaller scale than Earth, but you can get mods that make it like Earth, and it makes the game so much harder. Anyway, let's say we're looking straight down on our planet. So we're looking right up here at those ice caps. So I'm not going to draw them because we're just going to pretend we're little ways in the future. That might have been too dark. Okay, here's the sun. Now, first thing that I want you just to think about is we're looking straight down on it, right? Okay, what I want you guys to determine initially is I know that our planet orbits the sun. I'm good with that. But I also know that our planet spins along its own axis. I want you guys to reason out over the next minute or so, does it spin like this, which we'll call option A, or does the Earth spin like this, that we'll call option B? Again, I want to stress we're looking straight down from north. I'm going to help you out with this if need be, but I want you guys to talk about it. Which way does the Earth spin? Option A or option B? First one, we know that the sun, as you look from, this Earth, as you look from north, spins like this. Now, I'm going to draw, not to scale, our moon floating out here. I'm going to use a better color so I can actually see it. Ugh. Okay, there's the moon. As we look at this, I always struggled with this idea because we're going to try to launch a rocket. Now, there's two perspectives that you can think about with this, and it's kind of strange. Hypothetically, and I'm going to put this line inside instead. So I know the Earth spins like this, as we're looking from the north. Okay, 2 options to launch. Let's say I'm going to launch something here. And I guess before we explain it, what did you guys think? Do I launch toward the east or do I launch toward the west? So when you say launch toward the east, and this is a weird perspective thing, should I launch with the rotation or against the rotation is what I'd rather think. With. So we have 2 different options. And I can see the logic behind both of them, which is why this has always confused me. If I were to launch with the rotation, I'm already going, and I'm going to pretend I'm at the equator. If I'm launching that direction, I'm already moving like 1,000 miles per hour because I'm at the equator and the Earth is spinning. So if I want to go faster, if I launch this direction, my velocity in the end is going to be the launch plus the spin. So I'm like adding velocity to it, right? So here's what's weird and where my logic, like, it just breaks down, and honestly it still kind of does as I think about it. Because that makes me go the fastest relative to the sun, relative to the moon, yeah? Now, in contrast with that, if I were to launch the other direction, and I'll do it from this side of the planet. So let's say I were to launch this way, and I'm just going to pick up some numbers. Let's say I launch at, and we're going to make up a number that acceleration would kill people, but we're not really doing this. Let's say I launched at 5 kilometers per second, and the Earth is already spinning. I have no idea how many kilometers per second, 1,000 miles per hour. I'm going to make up a number. This is not a real number, okay? Let's say it's 10 kilometers per second. That is nowhere near as fast as it really is, but we're just pretending it is. Okay, my overall speed relative to the sun that's sitting still is 15 kilometers per second, right? Relative to the ground, how fast does my thing launch? What do you guys, 15 relative to the ground? If you're riding on a bus and you jump forward or you walk forward at 5 meters per second, relative to the bus, you're only walking at 5 meters per second, right? So I'm really only going relative to the ground at 5 meters per second. Now, that seems kind of slow. When I launch this way, if I do the same thing and I launch at 5 kilometers per second, but the Earth is spinning this way, right, at 10 kilometers per second, then I think that one almost looks like I'm going at 15 kilometers per second relative to the Earth's surface, because I'm already going 10 past it, and now I'm just speeding up the other direction again. Turns out, we don't really care about just relative to Earth. We do, in fact, care about relative to everything else. We want to launch the direction of the Earth's spin, which is why if you're in Florida at Cape Canaveral, when they launch over the ocean. They go toward the east. Cool. Weird ideas. I can see the logic behind either one. I'll tell you from experience of my own space program, launching opposite the rotation is much harder. Yep, we had that discussion. Much harder to get orbit if you go the opposite direction. I can see it either way though. Cool? All right. Next thing that we need to look at 18 really quick. What's up? Yes, so we generate gravitational fields, and everything does. Now, there's a few different ways we can think about gravity, right? I know that any 2 objects in the universe attract each other, but literally any single object also attracts everything else around it. Doesn't matter the other's mass, like I know that it does pull toward it at a certain amount. So as we look at these, we are looking on number 18, we're given a few different things. I know, and I'm going to draw a picture of it. I know they have a picture for us. I know that the mass of the Earth is, I don't know it off the top, 5.97 times 10 to the 24th kilograms. The mass of the sun is 1.99 times 10 to the 30 kilograms, which scientific notation is always misleading because this doesn't seem like that much bigger, but notice it's literally times a million. Like a million times more massive, because 10 to the 6 is the difference. Okay, what else do we know? And if I'm going to try to draw a 2 scale, roughly. Here's the sun. The Earth, I'm going to say, and I'm guessing here, but I'm going to say the Earth is probably about there. And the moon would probably be about here. Okay, looking at this, as I look at it, I'll tell you, I do think that I'm way too close still, just for the record. Now, we have a way to calculate the gravitational fields that something produces. Now, we saw the other day on Earth that the acceleration of Earth is exactly equal to g for our planet when we're on the surface, which we saw we get further away, the acceleration due to gravity, or the force or the gravitational field strength gets smaller the further away you get. Now, as we look at this, we are given some other values. The radius that we're looking at here can be kind of misleading. We are given this distance between the Earth and the Sun, and what were we told it is? 1.497. So this drives me crazy. Did you guys hit scientific notation hard in any of your classes ever? So scientific notation, it's convenient for like large numbers, right? Like it makes sense to use. Usually, and not usually, always you pick a number between 1 and 10, and then you make it times 10 to some power. It drives me crazy that they have 14 point something in scientific notation. I'm going to change it because it annoys me so much. Instead of 14.96, I'm going to say 1.496 times 10 to the... I have to add another one. 10 to the what then? 8 kilometers. Okay. Now, furthermore, I'm told this distance from the Earth to the Moon is what? That's 3.9 times 10 to the 5. Okay. Now, looking at this, couple things. If I want to know how hard does the sun pull on the moon and the Earth pull on the moon, right now I think I have all the information I need for the Earth pulling on the moon, because I know how far away the moon is from Earth's surface. I want you to grab your calculators real quick. If I wanted to know how far the moon is from the sun's surface, it would have to be that whole distance, right? Do me a favor real quick and add these up on your calculator and see what you get out of it. I'm going to write the radius from Earth here as 3.9 times 10 to the 5. But I want you guys to add up the sun to the Earth and then the Earth to the moon again. And just let me know what your calculator gives you. What's that? What do you guys come up with? Not a lot of confidence in that. Okay, so I agree. I'm going to look at yours, Felicia, because I had to come get my calculator just to see one thing. What did you do between these? What should you do to take that first distance? Say it again. Nope. Let's just add it. So here's the cool thing. I'm going to claim the sun is 1.5 times 10 to the 8th kilometers away from the Earth. What do you get when you do it again, when you add them up? Is it still 1.5 times 10 to the 8th kilometers from Earth? It's still the same number, right? So it's because the distance between these planets is insane. Between our Earth and the sun, it's huge. We're adding almost nothing, although it's a huge distance still. As astronomically speaking, it's almost nothing. It's still 1.5 times 10 to the 8th. Okay, so the first problem, it asks, hey, find me the ratio of the gravitational strengths, and it's sun to Earth, I believe. I'm going to reread this. Find the ratio of the gravitational fields due to Earth and the sun. I'm going to go sun to Earth. So hook it up. We need an equation. We're trying to find a ratio. Is there an equation that tells us the strength of a gravitational field for an object if you know its mass and the distance away from the center of that object? Well, golly gee, I think we do. How do you find the gravitational force? It's our constant times the mass of whatever you're looking at divided by the distance between them squared. So we're going to go a step further. Check it out. You guys, I can never remember, and I'm sure I ask this like every 2 weeks. Do you plug in values and then calculate, or do you calculate and then plug in values? Do you plug in at the very beginning or the very end of a problem? Both? Okay, so check it out. We are asked to find the following. I want to find GS over GE. the gravitational strength of the sun on the moon over the gravitational strength of the earth on the moon. Yes. So let's check it out. I get G. What mass do you think I should use if I'm trying to figure out how much gravitational field strength the sun exerts on the moon? Or any body, really. The mass of the sun. Over, and you do not have to write this because this is awful, it's the radius from the sun to the moon. And I'm going to write my square here because I think it looks a little nicer. This is the numerator. That's how you find the gravitational strength that the sun exerts just on the moon. Now, when you guys are thinking on your projects, I'm okay if you use G m1 m2 over r squared. I'm good with it. Cool. All right, on the second one, how would we make this equation work for the Earth, which is a blue planet? So we'll go ahead and use blue here. It'd be G still times what? The mass of the Earth over r squared, where r represents where to where? Earth to moon. Have I lost anybody yet? Okay. I don't like complex fractions, which is fractions with fractions. Don't love them. What would I do instead of dealing with a complex fraction? One more time. The reciprocal. So I'm going to leave this notation that's really specific behind. I'm not going to write the words. I think that this becomes, in the numerator, I will just write GMS for sun over the radius from the sun. Times, what's that reciprocal going to give me? G times mass of the Earth. Anything convenient happen? Well, G. I think we can calculate this. We have 4 numbers. When I did it, because I like things to look nice, I did this, RE over RS, I just rearranged it, and then that got squared, times the mass of the sun over the mass of the Earth. Calculate that for me real quick. If you've already calculated it and you got 2.2 or 2.3, I'll take it. I'm good with that. So here's this one. To find the net force on the moon. Right now in this nice system, what are the only things acting on the moon? Due to where? From where? Earth and sun. I bet that we could just do the gravity, the strength of the field from the sun on the moon, plus the gravitational strength of the Earth on the moon, and you're going to get a small number. I need to look at my calculator because I don't trust your book. Is it 2.6 times 10 to the negative 3? (2.6 times 10 to the negative 3), or if you'd rather, on my calculator, spit out 0.002618 newtons per kilogram. Now, the cool thing about this is it's easy to like misrepresent and maybe not quite get what this is saying. For every single kilogram, you pull with 0.003 newtons. There's a lot of kilograms in these things, right? In the moon, for example. So as we're looking at these, the actual strength of the force that you're looking at, for every kilogram that the moon weighs, it's pulled toward the sun and the Earth with that many newtons times the mass. Yep. Good. Sweet. I will take that. All right. We have 20 minutes remaining. With those 20 minutes, if you are completely done with stuff, I'm going to say continue working on the calculations on the back. Just to check, because I haven't gone into your guys' stuff in there, did y'all make copies from the Canva of your own so that people wouldn't delete it? If you open it, if you go on the very top, there's still file, and I can show you, but there's just a make a copy. But I haven't looked at it. If you guys want to, when you submit them, if you want to just make a copy and submit it to me, I can show you maybe a better way, and I will show you a better way. So here's mine, and I'll come back to you. When you're submitting these, so let's see, here's the blank one. Up here, when you're looking at it, there's a share option. So like this is mine, and I know that nobody else has been working on this one because this is mine, and I didn't share this one with you. But if you click share, you can download. You can download it. You get to choose how you want to download it. PNG is nice if I'm going to print. PDF print is fine. I will be going over to the elementary this afternoon to print them, and as long as they're all there, I can get them all. I will not laminate them until you guys have had a chance to write all of your stuff on the back or to glue or whatever your stuff is. I would save it as a PNG and then submit it to the Google Classroom. Okay. For that, if you think that you are not going to submit it, I'll change the due date in the classroom. But if you think you're not going to be able to submit it today on time, please let me know and not make it a surprise so that I can just go do this big print one time. If your group is done and you have nothing else to work on right now, I have tasks for you, but I'll wait until your group tells me you're done, and then I'll have you go do it. Sweet. I'll come around and take the homework. You guys get some time to work on stuff. Travelers, I haven't gotten a lot of reaching out from you guys. If you have questions about anything, please do reach out. Remember, let me rephrase that. Please submit your picture of your homework via email. Cool.